studying numerical differentiation and integration. So in the previous lecture we studied the differentiation, how to calculate the first derivative and the second derivative using the numerical differentiation, or you can say the central difference methods, or you can say the difference methods, which were backward, forward, and central differences. So now here we will study how we can calculate or do the numerical integration. So the numerical integration is, you can say, have encountered this in the very, you can say, the wide range of applications. All right, so basically this one, the f of x, is basically called the integrand, and these a and b are the limits of integration. The value of this definite integral is the area of the region between the graph f of x and the x-axis bounded by the lines a and b. Right, so I think this one is the very common interpretation of the integration, that it is the area under the curve of graph, and that is bounded by the limits which are defined by these limits of integration. Alright, so we have an example of the definite integral, which is like the bending moment and the shear force in the beam. So the moments is basically the integrand, the difference in the moments is basically the shear force integrated at x1 and x2, which is equal to the difference at the moments at point 2 and 1, where m2 is the bending moment at position x2 and m1 is the bending moment at x1. In this case, the integrand is the shear force. Integrand is basically this function here, which is whichever is you can say being integrated is the integrand. The integrand may be analytically or as a set of discrete points. Alright, so basically this values, this term, the integrand, could be the function value. For example, as we have calculated in the differentiation method, so there could be different functions, e raised to power x, cos x, sin x, or whatever functions we ever have. Alright, so this could be a complex, you can say, functions, and it could be some data points. Alright, so for example, there is some data points. At different points we have the values and we don't know the function yet. Alright, so when on the similar note as we did in the differentiation, right, so we can really have the two methods. First is that if we have data points, we first get to know the function using the interpolation. If we know the best curve on the best fit for the points, alright, know first the best fit, find the function, and then you can say do the integration and follow that path, or really use these data points directly to find the differentiation or integration. Alright, so this is the way we commonly will go, that without getting involved in the analytical solutions, we will use only the information from the data points to, you can say, numerically calculate almost exact solutions. Alright, so here using the numerical integration could have like two purposes. One could be that the function, the integrand, is very complex, or the other could be that we have some data points available. We don't want to go the longer procedure and use the numerical method techniques to, you can say, approximate the exact solution. In order to carry out the numerical integration, discrete values of the integrand are needed. Alright, so this means that even if the integrand is an analytical function, it must be discretized. Alright, so if we have this kind of function here, complex function, so we need to put the values here. Alright, the 1, 2, 3. By putting the values, basically what we are doing is we are discretizing the function to be used in our calculations. So the normal you can say the technique is basically, the general technique is Newton-Cotes formulas. These are basically of two types, the closed form and the open form. Right? In the closed form, the data points at the endpoints of the interval are used in the calculations, and the trapezoidal and Simpson rules are basically a, you can say, the closed form, and the open form is the limits of integration extend beyond the range of the discrete data points. So the rectangular rule and the Newton-Cotes formulas these are the Newton-Cotes formulas that are based on the open form. So we will study first the open form here, and then we will study the closed form, which is the trapezoidal and Simpson's rule. So the open form is, you can say, the most basic one here, and the first one is the rectangular rule. Alright, so it says that if you want to find the integral of this function a and b, which has limits a to b, and function f of x dx is approximated by the area of the rectangle. Alright, so this is the f of a and this is f of b, and this rectangle may be built using the left point and right point, or the midpoint between the intervals. So this one is a interval a and b. So using the left point and the left hand point method, what we will use the left point and find the area under, you can say, the up to that point and area onto the graph. Alright, so basically how we find the area of the rectangle is, you can say, the length, this one length is basically b minus a. Alright, so this one is b minus a, and this is basically f of a, because this value is 0 here, right? So this value is f of a. So the area using the left end point is basically f of a into b minus a. Similarly, if we consider the right end point, this will be this shaded rectangle here, and we are using this point, f of b. Alright, so area under this rectangle here is basically on the similar note f of b minus f of b into b minus a. Similarly, if we can also use the midpoint, alright, so we have f of a and f of b, which are corresponding by the points a and b, so we can find the midpoint, which is half of a plus b. Alright, so we move to that point, half of a and b, and use that point to calculate the rectangle. Alright, so the area will be the function value similar to these two areas, the function value at that point multiplied by b minus a. So this one is the area under the rectangle. So the difference, what we said with the open form, is that its area is going beyond, you can say, beyond the limits of the integrand. Alright, so you can see that we are going beyond the limits of the integrand. So that's why it's an open form. So one thing you can notice here is that this method here specifically is not very accurate. For example, here we have left a lot of area which we haven't calculated here. Similarly, here we have left a lot of area, and here we have included, you can say, the most of the areas which shouldn't be included in the integrand. So to counter that, we normally use the composite rectangular rule. Composite means, you can say, multiple rectangle rule. So the idea here is we will use smaller and large number of rectangles and approximate the result, so that we, in the large areas which were neglected before, couldn't be neglected. So what we will do is, in the same interval a b will be divided into n sub-intervals. Alright, if there will be n sub-intervals, there will be n plus 1 points. Alright, so you can see that these are three, I will color it the different ones. You can see that these are three regions, three, you can say, sub-intervals. And this one orange, purple, and let me color this one green. Alright, so but the points here are n plus 1, because these are three sub-intervals, and but the points are 1, this one is 2, 3, and 4. Alright, so the number of points are basically 1 increased from the number of intervals. So each sub-interval is, so we have labeled these sub-intervals. The first point basically we said it is A because our limits are from A to B and the last point is B. Alright, so the first rectangle, or the first you can say the rectangle here will move from, you can say this rectangle, the first one will be labeled from the points, this one A and this one will be x2. Similarly, the last the points of the last rectangle. Similarly, for the last rectangle, we will have the end point will be B. Alright, so xn plus 1 will be equivalent to B. So over each subinterval, the integral is approximated by the area of the rectangle. These rectangles are constructed using the left end point, right end point, or the middle point. So the same techniques can be followed of the left, right, or midpoint as described earlier, but now we are not making a single large rectangle to be drawn for the area. Alright, so we are using multiple small, you can say, areas or rectangles to calculate the integral. So adding all these areas or the rectangles, we can approximate for the total value of this you can say integral. So the composite left end point rule or the rectangular rule will be this one. Right, so we have discussed the first point is A point and the second point is x2 and the third point x3. Similarly, this one is xn and this is xn plus 1, which is equal to B. Alright, so we have n rectangles or n intervals, then we have n plus 1 points. Alright, so this is similar to the, you can say, the previous areas we calculated. Alright, so the function value multiplied by B minus A, or the difference between those intervals. So here is the same, the function value at that point. If we are using the left end point, so we are using these points. Alright, so the left end points of our intervals. So left end point multiplied by the difference between x2 and x1, which is you can say the next point and the previous point. So this is basically based on the previous method. N will move from 1 to n here. Alright, so n plus 1 basically is not included here. So alright, so our interval will move from 1 to n and this one is basically there. So these are the differences. Alright, so we can use also the you can say the rectangles of different spaces. Alright, so if we use all the rectangles of similar spacing, then this B minus A could be easily divided by a fixed method. Or for example, like if B minus A is 5 and we do 5 intervals, alright, so this will come out to be 1. So we can for the equal spaces, this you can say that this difference will remain the same for all of the you can say all of the rectangles. So we can keep it out of the summation and use this instead. Alright, so this h can be calculated by the difference between these limits and divided by the number of subintervals we are using, or the number of rectangles we are constructing. Similarly, if we are using the rectangular and a right end point rule, then you can see that we have to start from this point. Alright, we have to start from point 2 and move towards point n plus 1. Alright, so our interval will start from point 2 and move to n plus 1, and similarly this will be the same, and the function value at that point and multiply by the difference. Similarly, if we have the same equally spaced intervals, then we can keep h out, and this one will be the formula. So what basically this formula is telling us that we need to calculate the function value at that point and then multiply by the difference. Alright, so this one is a midpoint. So for every rectangle we have to calculate its midpoint. Alright, so the midpoint is basically uh, given by this formula. Alright, so the next interval minus the previous interval divided by 2, and the areas are calculated in the similar pattern because we want to find the function value at the midpoint and multiply it by the difference in the x values. So if we are similarly using the equally spaced data points, then we can get the h value out, and this is basically the formula for our composite rectangular rule using midpoints. So this is example. So evaluate the following definite integral using all three composite rectangular rule strategies, and n is equal to 8. So we have to divide in 8 subintervals. Alright. So the difference, so you can see that we have to move from -1 to 1. Alright. So b is 1 and a is -1, and we have to find the spacing as we have to divide it into the 8 subintervals. So we will use this formula of the h. So b minus a is 2 and divided by 8 is 0.25. So 0.25 will be the spacing between each interval. So as there are 8 subintervals, so there will be 8 plus 1, 9 points. Alright, so we have discussed it in the lecture that we will have one more point than the number of subintervals. Alright, so our points will be, you can see that it will start from 1 and will have the difference of 0.25 because we have calculated the difference, which is h is equal to 0.25. So these are the points, and we will move to 1, which is x9. Alright, as we said that our first point will be a and our last point will be b. So this 1 is basically x9 and this -1 is x1. So f of x is 1 over x plus 2, which is this integrand. Alright, and we now know these points which we need to calculate, which were starting from -1 and moving from like -0.75, similarly -0.5, so on to 1. Alright, so using the left endpoint, and we can use the formula for the left endpoint, which will start from 1 to 8. Alright, so you can refer to the formula and get the function values at that points. Alright, so we will have to move 1 to 8. This one is basically x1, this is x2 and x3, similar to x9. Alright, so based on the formula we will put, so we'll have to calculate from bar I is equal to 1, this is f of x1. So we have to calculate the function value, which the function is 1 over x plus 2, I guess. Alright, so I'll just put the value of x here and get the function value at x1, x2 to x8. Alright, and this is the basically the integral value which we have calculated using the rectangular rule. Similarly, the right hand point, you know that we start from the second point and move towards the end point. So we'll start from function value of, we'll find the function value of -0.75 to this and use the formulas to calculate the value. Similarly, using the midpoints, you can find the midpoints. You can say you have to calculate for every midpoint. You have to calculate, then put this value in the function value, and then calculate, and you will get the answer. So this is how we use, you can say, the open methods to get the integral values. So we were looking at the numerical differentiation and integration, and we just studied the open form of calculating the you can say the integrands using the Newton-Cotes formula. So in the closed form, we studied that there are two formulas or the two methods we can use, which is the trapezoidal rule or the Simpson's rule. So the trapezoidal rule is here we have to replace the integrand Alright, so you know that integrand is this one, f of x is basically the integrand. You have to replace the integrand with a straight line, you can say the function of the straight line, the polynomial. Alright, so we have to use the first degree polynomial connecting the points a f of a and b f of b. So a f of a is basically 0.1 and this is 0.2. So you know that this one value was the function. Alright, so basically in the rectangular method we calculated the area of this. For example, if we use the left hand point method, we calculate this area. Right, so what we are doing is we this is the point a f of a. All right, so this is basically a and this is b. All right, this is f of a and this is f of b. So now what we will do is we will replace this function with the equation of the line joining these 2 points a f of a and b f of b, and then calculate this area. So this is basically the trapezoidal rule. So the equation of the line is given by this f of a, because we have to start from the f of a. Alright, so f of a plus f of b minus f of a, or minus, this is basically the slope, or you can say the m multiplied by x minus a. So this is basically the simple formula for the you can say the line from the 2 points. So we have to replace this polynomial. So instead of f of x, we replace this polynomial, first degree polynomial here, and we have put the formula of the first degree, or the equation of the first degree polynomial here. And if we simplify the expression, it will yield to this f of this formula, f of a plus f of b divided by 2 into b minus a. So this is basically the area, this is the trapezoid. So this is basically the trapezoid rule. So instead of finding the area of the you can say the rectangle as we did in the rectangular rule, we are basically finding the area of the trapezoid, which is given by this formula which we just calculated. So similar to what we did in the rectangular method, we can also use composite trapezoidal rule to considerably improve the accuracy of the our, you can say, solution. So in the similar manner, we will divide the interval into n subintervals, and similarly we will have n plus 1 points. Alright, so we will call the first point a and the last point b, and all the points will be named from x2 to, you can say, xn. Alright, so normally we use equally spaced data, but you can also use, you can say, different varied spaced data also. So we will calculate between these intervals. So for every points, for example, these for every point we will have a different, you can say, for every interval we will have one trapezoidal rule. For every interval we will have one trapezoidal, and then we will add the areas of all the trapezoids, or the areas of the you can say rectangles of trapezoids basically, so to get the final integrand. Alright, so this is basically, yeah, you can say how this operation will go. Alright, so for the first 2 points x1 and x2, we will have this equation, plus add for the second and third point this equation. Similarly for the third for the nth and nth plus 1 point, we will have this equation, and we are basically adding it to get the function value, because this is composite rule. So we can represent it with the summation here. So basically xi and the next one divided by 2 and xi minus 1. So this is basically the summation formula. So if we have equally spaced data, then we can replace this by h, and this is basically the formula for the, you can say, the general formula for the composite trapezoidal rule. So this can also be represented by, you can say, this open form also. You can say the more open formula, not the compact one. The general and the compact formula is basically this one. So here you can see that here we have f of x1 and f of x2 here. Similarly, you can see that f of x2 is also repeating in the next interval, and similarly we have f of x3 which will be repeating in the next interval. So you can see that the first and the last one are not repeating, whereas all these, you can say, internal values of f of x are getting repeated. So this can also be, you can say, you can intellectually, you can say, refer to this idea also, or you can open this one out and put the values from 1 to n and get this formula, right? So you can easily remember this formula, because here you can see that only the limiting values f of a and f of b are without this multiple of 2, right? So all other values we are multiplying by 2, and not multiplying the limiting values. So this is basically, you can say, the more easier formula to remember. So this is the example. So we can, if we have to divide in the 8 intervals, so in the similar manner we get the 8 intervals. This is our integrand. So this is basically the same example, so I'm not explaining it again and again. So we will just move on and come here. So this is the formula for the trapezoidal rule, composite trapezoidal rule. So we'll get the function value at a, alright, and similarly this is the function value at b and all the points here. So you can get the answer using the composite trapezoidal rule. Now we'll move towards the Simpson's rule. So this is the second, you can say, the method we use in the closed form. The trapezoidal rule estimates the value of the definite integral by approximating the integrand with the first degree polynomial. Alright, so the first degree polynomial is basically the line. Alright, so we use in the trapezoidal rule, and between the 2 points we draw a line. Alright, so any method that uses a higher degree to connect these points will provide more accurate result. Right? So Simpson's 1 by 3 and 3 by 8 rule respectively use second and third degree polynomials to approximate the integrand. Alright, so we will study the Newton-Simpson's 1 by 3 rule will use the second degree polynomials, and this one will use the third degree polynomials. So it will get quite complex if we want to know like how it is calculating it. So in evaluating this function, the Simpson's 1 by 3 rule, we will use a second degree polynomial. Alright, so for the second degree polynomial we will have to use 3 points, right? So you can refer to what we did in the interpolation when we studied Lagrange interpolation. Alright, so this is the formula for the second degree polynomial. So it is using x1, x2 and x3, 3 points. Right, so the limiting points and the midpoints are being used here. So the method is similar to what we did in the trapezoidal rule, that we have to replace this f of x by the polynomial. But what we did in the trapezoidal rule is that we replaced it with the single degree polynomial, which is a straight line. Right, so now we are replacing it with the second degree polynomial, which is given by this equation here. So we have to replace this f of x and put this value of p2 here. Alright, so if we do all the steps what we did in the trapezoidal rule, alright, so if I do it here, it will get very, very complex and you will not be able to get what I want. But the method is somewhat similar to what we did here. Alright, so we are basically summing up all the you can say all we can putting the values here and calculating these limits and simplifying the expression. Alright, so we are using the same here, and what we'll get is this formula. Alright, so it is, has, you can see that it is dividing by 3. Alright, so that's why it is called 1 by 3 rule. Alright, so h here is b minus a divided by 2. The similar you can see here is that these are the two interval values. Alright, so we are using these 2 points. Alright, so in order to calculate, you can say the accuracy of the trapezoidal rule can be improved similarly by using the composites method. Right, so in the similar manner we will divide the interval in you can say n in subintervals, and this is the h value, and we have to construct every, you can say, for every 3 values we will apply, you can say every 3 points we will apply this polynomial, then for other 3 points we will apply another polynomial, and for other 3 points we'll apply another polynomial, second degree polynomials. Alright, and then we will add these results to get our final integrand. So for the Simpson's rule, 1 by 3 rule, for the composite Simpson rule, one thing you must notice is, one thing you must keep in mind is that you have to divide using even numbers. Alright, so for example we are using x1 and x2, so it will use 3 points as x1 and x2 and the midpoint of x1 and x2. Alright, so I will write it as m1 2. Alright, so midpoint of 1 and 2. So it will draw the polynomial between these 3 points. So it will do it for x1 and x2, then x2 for x3, and then similarly x3 and x4, and so on. Similarly the end one will be the xn and xn plus 1. So it has to be the even numbers so that the composite rule can be implemented. Alright, for the composite rule we will sum up all the, you can say, equations. This one was for you can say x1 and x2, this one is for x1 and x3, and so on, and we get this expression. Alright, so one thing you can notice here is that there are terms with the multiple of 4 and there are terms which don't have any multiples. Alright, but these are repeating. You can say find the f of x3, you can find here also, you can find here also. Alright, so we can generalize this formula here, which is equal to h by 3, and f of x1 is similarly using ones, and similarly the last point f of xn plus 1 is you can say is coming only once. Alright, so but you can see that the multiples of 2, for example f of x2 and f of x4, similarly f of x6 will be multiplying by 4. So we can put the summation where I can move from 2, 4, 6, for example the multiples of 2 are repeated by multiplied by 4. Alright, similarly these the multiples of you can say 3 onwards odd numbers, so 3, 5, 7 are repeated twice, so they are multiplied by 2, whereas the first and last terms are being used on the similar note. So this is basically the generalized formula for the composite Simpson's 1 by 3 rule. So applying this on the same example, we will use because we have 8 intervals and these are our subpoints, so we will, this is h, right, so we will put it in the same h by 3 here and get the values of all the points in which we get it. So you can see that we are multiplying some points by 4 and some points by 2 and just calculate the value, and this one is basically the value of this function, the integral of this function. So on the similar note we have Simpson's 3 by 8 rule. Right, so the main difference only here is that instead of using a second degree polynomial, we are using the 3rd degree polynomial between a and b. Alright, So the first point is basically the A point, and the second point is 2a by 3, because when there are 3 points, for example, like we have A and B, then deciding the midpoint, and the third point is basically actually the midpoint. But now between A and B we have to place 2 points. This is A and this is B. We have to place 2 points. So this is basically 2a plus b by 3. Alright, so this is mentioned, x2 is basically 2a plus b by 3, and similarly a plus 2b by 3. So these are the 2 points we will place in between a and b, and make a polynomial pass through these two, and these you can say 4 points, which will give us the third degree polynomial. So on the similar manner, we will be replacing f of x with third degree polynomial. The third degree polynomial function using the Lagrange interpolating formulas can be given by this. So we will put this function here and simplify the results, and then we can get this, you can say, formula for the Simpson's 3 by 8 rule. You can see that it is multiplying by 3 by 8, so that's why it's mostly referred to as 3 by 8 rule. Alright, so similarly we will also have to calculate it in the composite form. Alright, so in the composite forms all the procedure is basically the same. So for every, you can say, interval, it will calculate the 4 points. So it is really quite complex. So for example, subintervals f x1, it will calculate for. So here you need to make sure that your subintervals are multiple of 3. So if you apply the composite 3 by 8 rule, then we can see that this is the expression we can get, and here you can see that some of the expressions, especially the f of x1 and f of x n plus 1, are repeating only once. Alright, some are the multiples of 3 and some are repeating twice, similar to what we did in the Simpson's 1 by 3 rule. To calculate the general term, we can you can say simplify it using summations. So 3h by 8 is common, which is already common, so it's outside, and f of x1 and f of xn plus 1 are repeating only once, so we just put it aside. Then you can see that these two are repeating the multiples of 3. Similarly, this is repeating the multiples of 2. So these are put it here, and you can use this formula to calculate or use the Simpson's 3 by 8 rule to get the value of the integrand. So that's how we use the numerical integration to get the value of the integrand without even solving the exact, or without even solving for the exact solution or the analytical solution.